Hello, everyone, and welcome. Today we're going to talk about prescriptive optimization. My name is Jimmy Garrett. I'm a manager here on the sales engineering team. And yeah, we've got a fun one. I think this is a really fun topic. It's one that can be intimidating for people that aren't familiar with prescriptive optimization, that they've never taken a stats class. Maybe you've even just been afraid to open up that tool category. Oh, or perhaps you've dropped that tool onto the canvas and been a bit overwhelmed with the amount of options. So today's going to be perfect for you. We could go in depth in prescriptive optimization if we wanted to. Today, however, we're really just going to scratch the surface. So my goal for all of you today is to walk away from today's session understanding what prescriptive optimization is, what are some example use cases that you can use for prescriptive optimization, and then also how to configure the prescriptive optimization tool. To illustrate prescriptive optimization, we're going to walk through a very simple use case today. We're going to start with that use case outside of Alteryx, so we're going to spend a decent amount of time just making sure we understand what the problem is. We're going to visually represent the problem. We're going to make sure that's all squared away and we know what the answer is to this optimization problem. And then we're going to take it over to Alteryx. Because there are a lot of configurations for that prescriptive optimization tool, it really helps us to understand what's going on if we know exactly the problem and how to solve it before we even get to Alteryx. I realize that there are probably a lot of personas here today with us. Imagine we have data analysts, we have statisticians. Just know that this session is for all of you. For the data analyst, I imagine you're going to learn a lot about prescriptive optimization today. For data scientists, statisticians that perhaps already know what prescriptive optimization is, today you might just understand how to configure what you already know into Alteryx. Yeah, hope that anyone on the call today is going to leave here with more information than when they joined. All right, so before we get going, let me define what optimization means, or how we're going to define it today. So optimization is making the best of a given scenario that we have. For example, let's say that we own a restaurant or we manage a restaurant, and we want to ensure that we have enough wait staff to manage all the tables, but we don't want to have more staff than necessary because staff is obviously a cost. The more people that are there on staff, the more money we're having to pay. We also don't want tables to be unhappy waiting a long time for the staff to come serve them. That'd be a perfect use case for optimization. In this case, we would want to minimize the number of employees, our staff, while still being able to provide for anyone that comes into the restaurant. Another example of optimization could be if we are, let's say we sell some products. Maybe we sell some dry goods, and we have so many linear feet of shelf space at a grocery store. So what we need to do is we need to maximize our revenue of that shelf space. But we might have some business rules where if we have 4 products, maybe we need to devote some portion of that shelf space to each of those 4 products. Those 4 products obviously have a cost associated with them. They have a price that we're going to obtain if somebody purchases a unit. So again, optimization is going to be a way where we can maximize our revenue of the shelf space given all of those other factors at play. Today inside of Alteryx, it's really going to be a one tool example. So we're really only going to need to configure one tool as we go through today. So that in itself sounds easy. And hopefully after we get through all the talk about the problem ahead of time, you'll agree that it is easy. Today we're probably not going to make any forward-looking statements. If I do, just know that you shouldn't base any purchasing decisions based off things that don't exist today inside the product. All right, a little bit about the agenda today. We're going to spend a lot of time talking about that workflow background. We'll touch on some key concepts. We'll go through the optimization problem, and then we'll talk about how to configure the optimization tool. So those first 3 bullets are going to be outside of Alteryx. That 4th bullet is when we're going to move over and configure the optimization tool inside of Alteryx. If you aren't already on the community, let me encourage you guys to go sign up for the community today. There's a ton of great information out there. I use the community daily to search for answers to questions that I have. So any Alteryx related question, you can go type that in, see if it's already been asked and answered. If it hasn't, you can add in your own question. We have a lot of eager members of our community who are customers, who are employees of Alteryx, that want to help. So please go connect with them out there. You can also get access to macros that people create, analytic applications. There's a ton of information out there. And then finally, the last thing I'd like to plug is the Alteryx Academy. We've got free interactive lessons, free live training. My favorite, the weekly challenges. The weekly challenges give you a workflow that contains a prompt, it contains a starting data set, and it's up to you to use the tools of Alteryx to make that starting data set look like the ending data set. People post their answers, you can see how they solved it, you can compare it to yours. It's a fun way to learn Alteryx and learn other areas of Alteryx that you might not use day in, day out. And who doesn't love to get certified in something that they know? Have a little digital piece of paper proving that yeah, you know how to use Alteryx. That is available on our Academy as well. All right, so now let's start diving into the fun stuff. We defined what optimization means. We haven't defined what the prescriptive portion of prescriptive optimization means. So there's a lot of different types of analytics. I'm sure that you guys probably don't go a day without seeing the term analytics. There's descriptive analytics, there's predictive analytics, there's prescriptive analytics. Let's just take a moment and define the 3 of those today, right now. So descriptive analytics, it's describing what's happened in the past, things that you already know to be true. This could be in Alteryx done via the summarize tool. So if you did a group by statement, an account, or an average, something like that, using the formula tool. So essentially you are creating data based on things that have already happened. Predictive analytics takes it a step further. It takes what's happened in the past, but also either tries to make a prediction about what's going to happen in the future in, say, with time series tools, or with the traditional Brown predictive tools that can tell you variables impact on a target variable. Prescriptive analytics, on the other hand, answers what you can do. So whereas regression, in that regression example that I said, it tells you the variable's impact on the target variable, but it doesn't tell you anything about how you can affect or change those independent variables in order to get a desired outcome in the target variable. Prescriptive analytics not only tells you the impact, but it'll also tell you what you need to do in order to maximize or minimize that target variable. So in our example that we went through earlier, it tells you how many people you need on your staff in order to minimize labor cost, or what product mix do you want on your shelf in order to maximize revenue. So it is prescriptive in its result. All right, let's walk through this use case. I'm going to read through this with you guys. It's important that we are crystal clear on the use case. This is what I want to make sure that we understand what the problem is and what the answer is before we move over to Alteryx. So We're going to be talking a lot about these numbers that you see on the screen, the variables. Again, we're going to do this so that we can make sure we understand the problem outside of Alteryx. That'll make it very easy when we go over to Alteryx. There is a clothing manufacturer that has 750 square feet of cotton and 1,000 square feet of polyester. Each pair of pants that we make requires 1 square foot of cotton and 2 square feet of polyester. Every jacket that we make requires 1.5 square feet of cotton and 1 square foot of polyester. So let me stop there. What we've been told thus far is that we have cotton, we have polyester, and we have some quantities of that. We also know now that we manufacture pants and jackets. And pants requires both of the fabrics we have, cotton and polyester, as do jackets. Jackets require some of both cotton and polyester. And they have different requirements of those fabrics. Okay, let's continue. Due to manufacturing restrictions, no more than 400 jackets can be produced in a day. And a minimum of 200 pair of pants are required to be manufactured. Okay, so now we know some maximum values and some minimum values. I can't make more than 400 jackets. I have to produce at a minimum 200 pairs of pants. Okay, let's keep going. The price of the pants is fixed at $50. The price of the jacket is fixed at $40. Okay, so we know our revenue that we're going to obtain from each of those, and it's not a variable, it's fixed. So given all of that, our question that we're answering today, what is the number of pants and jackets that the manufacturer must give to the stores so that these items obtain a maximum sale? In other words, how many pants and jackets do we need to produce to maximize revenue? So we've got 2 variables we're solving for, the number of pants and the number of jackets. And we have a lot of other constraints and rules that we need to take into account. It is important to note that these relationships are linear. More on that here in a second. And that's it. We understand the use case now. We're obviously going to break this down a bit further as we go through because there's a lot of moving parts there. Some of the key concepts that we're going to talk about today, we're going to focus on linear programming. There are other options inside the optimization tool. We're just going to focus on this one today. We will configure the optimization tool in 2 different ways. One, manually, like you see in the box on the left-hand side of your screen. The other using matrices. That is on the right-hand box that you see on your screen. So we will walk through both of those today. So what you see on your screen right now, that's the entirety of the workflow we're going to walk through today. Okay, let's step through this problem bit by bit here. So what you see on the top left, I just read that to you guys. Not going to read it again for you. At the bottom, again, let's remind ourselves what we're doing here. What's the number of pants and jackets that we need to produce to maximize revenue? So there's only those 2 variables that we can affect, the number of jackets we produce and the number of pants we produce. Today we're going to talk about pants as X, and we're going to talk about jackets as Y. The reason why we're doing it this way is later we're going to graph these on the XY plane. So we'll have X and Y coordinates. We'll start drawing lines that show us the possibility of production for both pants and jackets. And we're going to be using our XY coordinates. So for today, we've assigned X to pants and Y to jackets. When we move over to Alteryx, we could use P and J to keep it easier on us, but for now we'll use X and Y. All right, so the next step that we need to do is we need to identify the objective. Our objective here is we need to maximize sales. So let's think of what is the equation for sales. Well, we know that we get $50 for every pair of pants that we create, and we've set pants equal to X. So 50 times X equals our total revenue for pants. We get $40 for every jacket that we sell, and we set jackets equal to Y. So we get $40 for every jacket or Y that we sell. So if we add the two together, we get our objective function. Our maximized sales is equal to 50X, 50 pants, plus 40 jackets, Y. And what I'll do here in the slide is I'll start highlighting things on the left-hand side and crossing them out, just so that we can make sure that we're covering off all of the elements, all the numbers that we see on the left-hand side. And what we could do at this stage, given that we have 50X plus 40Y, and we know we want to maximize that, what we could do is we could start picking out some numbers and just doing this by trial and error. Obviously, I know I can't just plug in infinity for X and Y. That would obviously be the maximized sales, but given my constraints, I'm going to run out of cotton, I'm going to run out of polyester, and I also have the 400 jacket and 200 pants constraint. But we could start picking out some values for X and Y and just checking to see, does it fit those conditions? Does it violate anything? And log its number of what revenue is and keep going. This would obviously take a lot of time, would take a lot of effort. I know for me, it would take more patience than I have. I'm not willing to spend the time doing all of that. And that's where Alteryx is going to come in handy. At the end of today, you're going to be able to plug this problem in very easily and get a result. All right, our next step that we need to do is we need to identify the constraints. Our constraints are, we only have so much cotton. We have 750 square feet of cotton. And we only have so much polyester. We only have 1,000 square feet of polyester. So for our constraints, we need to, from a generic sense, identify what can affect our decision variables. So in our example, let's get a little bit more specific. What can affect the number of pants and jackets that we produce? Well, what you'll see on the bottom right there in that graph, or that chart rather, is that on our first row, we lay out the information regarding cotton. So on the right-hand side, we have 750 square feet available of cotton. If I make one pair of pants, I know that I'm going to lose 1 square foot of cotton. So if I make a pair of pants, my 750 now goes down to 749. If I make another pair of pants, it goes down to 748, etc. For every jacket that I create, I'm going to lose 1.5 feet of cotton. So if I create one jacket, that goes down to 748.5. If I make another jacket, that goes down to 46, 47. Someone check my math as I go through today. I'm sure I'm going to make more mistakes if I try to do things in my head. And it's the exact same thing for polyester. So for polyester, we have 1,000 square feet available for every pair of pants I create. You can subtract 2 from that 1,000. For every jacket that we create, we can subtract 1 from that 1,000. So those are our constraints. As we increase the number of jackets and pants we're producing, we're decreasing the availability or the quantity of available fabric for cotton and polyester. All right, so we've identified the constraints. What we now need to do is convert those into formulas. Converting those into formulas is going to help us to visually graph this, as well as input the necessary information into the prescriptive optimization tool when we're configuring that inside the Alteryx designer. So our cotton constraint is X plus 1.5 Y is less than or equal to 750. Let's talk about that for a second. Let's talk about where we got that equation. So if you look at that first row in the chart right above that cotton constraint that just appeared on the slide. It says cotton, and then it says 1 square foot underneath pants. That's where we get X. So that X in the cotton constraint, you could think of as 1X plus 1.5Y. We got the 1.5Y from, again, the first row of the chart above. In our cotton constraint, we know that for every jacket we produce, it takes 1.5 square feet of cotton. So that's where we get 1.5 times Y, which is our jackets. And now let's talk about that operator, less than or equal to 750. The reason why it's less than or equal to 750 is we don't care if we don't use all 750 square feet of our available cotton. If we use 748, if we use 740, we'll have some leftover cotton, sure, but if it maximizes our revenue, then that's fine. Now, let's say that we worked for a company that was very environmentally conscious and they didn't want to have any waste. Well, we might need to then change that operator to say X plus 1.5 Y equals 750. That would ensure that we're using the entire allotment of the 750 square feet. But that wasn't a constraint in our example, so that's why we said it's less than or equal to 750. We know that we cannot go above 750, is what that says. Our polyester constraint is 2X plus Y less than or equal to 1,000. With our polyester line in the graph above, we could do the exact same thing. So we know that for every X, pants, we take 2 square feet. For every Y, jacket, we take 1 square feet, add the two together, and that has to be less than or equal to 1,000 square feet because that's all the polyester we have. All right, so now we have our formulas for the cotton constraint and for the polyester constraint. All right, let's graph these. So let's take those constraints and let's put them on our graph that we see on the right-hand side. So who here remembers the equation for the slope of a line? So I don't know about you all, but from my first algebra class that I took, I don't know, way back when, this was drilled into me. It was one thing that they repeated over and over at us. We had to write it down. We had to solve for the slope of a line countless times. If you don't recall it, I'm sure when I say it, you'll remember it. It's y equals mx plus b. So y is our value on the y-axis, equals m is the slope of our line, x is the value on our x-axis, and then b is the y-intercept, so where the line crosses the y-axis. And so now the exercise that we need to do is we need to convert our cotton constraint formula so that it takes the format of the y equals mx plus b. If we can get it into the slope of a line, the format for slope of a line, then we can plot it and we can visually represent that over on the right-hand side. That's going to be useful for understanding what the potential values for production are. All right, so I clicked the advanced button and you can see that all that math just happened for me. For those that are curious, what we first did from that top line to the second line is we moved x from the left-hand side of the operator to the right-hand side. So subtracting x on both sides then gives us that second line, 1.5y less than or equal to negative x plus 750. We need y to be isolated, so what we do is we divide each side by 1.5, and that's how we end up with y is less than or equal to negative 2/3 x plus 500. So we can now graph that. So the y-intercept is 500. So if you look on the vertical line, we cross that line, that y-axis at 500. And then our Slope is negative 2/3. And then whatever value we plug in for x, we obviously then know the value for y. But the triangle that you see on the right-hand side, that's green, the top right quadrant, that's what we can produce jackets and pants given our cotton constraint. So given the 750 square feet we have of cotton, we know that we can produce any combination of X and Y, pants and jackets, that fit in that green triangle. There's obviously more to consider. We need to consider our polyester constraint. So the equation for our polyester constraint is 2x plus y less than or equal to 1,000. To isolate y, what we need to do is subtract 2x from each side, so we get y is less than or equal to negative 2x plus 1,000. Negative 2 is the slope, 1,000 is the y-intercept. Plotting that on our graph, you can see that we have now modified the green triangle that was there after our cotton constraint. And really what we've done is we've removed the right-hand portion of that green triangle. So now given our polyester constraint, we have fewer combinations that are available of pants and jackets that we can create. Whatever's in that green shaded area, that's what we can potentially produce given our fabric. Remember, we have a couple other considerations to take into account, but right now, this is what's possible. All right, so we know what's possible given our fabric, given our cotton and polyester. Now let's look at what happens when we introduce our bounds and limits. You can think of bounds and limits as business rules. Are there any restrictions that anyone's placed on you? Generally from a business standpoint, we don't have more than 750 and 1,000 square feet of fabric. But we also have what seems to be some arbitrary business rules that we need to follow. So again, everything on the left-hand side that's been crossed out, we've taken care of already. The things that are left, the things that have not been crossed out, we still need to introduce into our graphical representation. So in our example, and again, I'm going to read on the left-hand side there, no more than 400 jackets can be produced in a day. That's just due to manufacturing restrictions, whatever those are. And we have to produce a minimum of 200 pairs of pants. So no more than 400 jackets, a minimum of 200 pants. So if we look in green on the bottom right, you can see what the equations are for each of those. So our jackets, Y, needs to be greater than or equal to 0. We can't produce negative jackets. I can't produce -1 jacket. I have to produce no more than 400 jackets. Or maybe a better way of saying that is, I cannot produce more than 400 jackets. So Y is less than or equal to 400. So it's 0 or above, all the way up to 400. So anywhere between 0 and 400 is possible. For pants, we have to have a minimum of 200, but there's no maximum given the constraint. So I'm sorry, given our limit and bound, I should say. So X has to be greater than or equal to 200. Okay, so let's take those over to our graphical representation and let's see what happens to our graph when we introduce our bounds. So we said that Y has to be greater than or equal to 0. Well, that animation was kind of hard to see. The horizontal line at 0 that intersects the Y-axis at 0, which is really just the X-axis, that turned green. So we know that Y has to be in one of the upper quadrants. Y has to also be less than or equal to 400. So you can see when we put that line onto the graph, we lose a tiny little sliver in the top left of what is possible. So we now have some combinations of values of pants and jackets that are no longer possible given our bound of 400. X also has to be greater than or equal to 200. So what's going to happen whenever I advance this is we're going to see another portion of that green box, or that green, whatever that shape is, disappear. So everything to the left of that line that we just drew, we know is not possible. So now, everything that you see in green, we know is not only a possible combination given the amount of fabric we have, but it also passes our bounds. It passes our manufacturing rules. So anything inside that green area, we can produce that. Generally, when we're maximizing, in this case revenue, it's probably going to be one of those points that you see at the top left, kind of the diagonal where those two constraints meet, or the point on the right. That's going to be the location of the combination of pants and jackets that will optimize our objective function. But we can confirm that, which we're about to do right now. So let's find what that maximum, what the combination of pants and jackets that we need in order to maximize our revenue. So again, that shaded area, that's all possible. Those combinations are feasible for pants and jackets. So what we can do now in order to solve this is we can take those constraints, the negative 2x plus 1,000, the negative 2/3 x plus 500. Remember how we took polyester and we took cotton and we flipped the equation so that y was isolated? Well, now what we can do is we can set those equal to one another. And that's the equation that we see on the screen currently. Well, let's solve for x. So first what we do is we subtract 1,000 from each side. So then on the right-hand side, we now have negative 500. So our equation is negative 2x equals negative 2/3 x plus 500. If I move x over from the right-hand side to the left-hand side, I add 2/3 x. So negative 2x plus 2/3 x gives me negative 4/3 x equals 500. Now if I divide both sides by negative 4/3, I get x equal to 375. So I know to maximize revenue, I need to create 375 pairs of pants. So what I can do is I can just plug that x back into either of those equations, negative 2x plus 100. I could take negative 2 times 375 plus 1,000, and that gives me y equals 250. So there's my combination. My combination is 375 pairs of pants and 275 jackets. That's going to optimize my function, which is the maximum revenue. And if we look at that on the graph, you could see it's that point where those two lines met. So that is our optimized point. If we plug both of those values, the 375 and the 250, back into our objective function, so remember the objective function, that was 50x plus 40y. We get $50 for every pair of pants. We get $40 for every jacket. If we plug the 375 and 250 back into that equation, at the very bottom there, you can see we get $28,750. That is our maximized revenue. All right, so everything we've done thus far, we haven't touched Alteryx. We understood the problem. We understood some new terms. We solved that problem using our graph, using a little bit of algebra. We figured out the answer. We could do that a lot more quickly using Alteryx though. So now let's take that problem that we fully understand and let's hop over to the Alteryx designer. Before we actually jump into the designer, let's talk about the configuration that we're going to see whenever we do go over to the Alteryx designer. So first of all, The first choice that we're going to make is we're going to enter the model manually. So everything that we enter, we're physically going to put into the configuration. We're not going to reference any data that's fed into the optimization tool. More on that here later, because we're going to talk about how we could feed it in via matrices, and we'll talk about the pros and cons here as well. We're going to use the problem type linear program. There were no quadratics in there, so this is the only one we're going to talk about today. We can then choose the solver. We give you some options for which solver to use. That's really outside of the scope of today, talking about the different solvers. Just know that if you do have a preference, you can select from more than one solver. Today, we're going to leave it with the GLPK. And then where it says maximize objective, just make sure that that slide bar has been selected. We want to maximize revenue. We don't want to minimize revenue. If we were solving the example that I stated earlier, which is the wait staff example, where we wanted to have as few as wait staff as possible on, while still making sure that all of our customers are adequately served, we would make sure that slider is deselected because we'd want to minimize the objective. All right. So then moving on to the constraints tab, this is where we'll enter those two equations, our x plus 1.5y less than or equal to 750, our 2x plus y less than or equal to 1000. That was our cotton and polyester constraint. It's important to note that the x and y, or whatever variables you choose, those need to be on the left-hand side of that equation. So don't have those solved for y. Make sure that any variable you have is on the left-hand side of the operator. And then finally, in the configuration, we need to choose our bounds and our types. I'm sorry, we need to enter our bounds, I should say, and choose our types. So our bounds, that was X, pants, greater than or equal to 200, Y, jackets, above 0, under 400, or 400 or under, I should say. And then there's the type. So what type of bound is it? It could be binary, yes or no. Are you making pants? Yes or no. Or really in our example of hiring staff, is this person coming in today? Yes or no, 1 or 0. It could be continuous, where it could take on any number, so even decimals, or it could be an integer. Integer is only whole numbers. And before we flip over to the designer, let's talk about our tool outputs. You can see we have 3 anchors on the right-hand side. S is our simple data output. Well, look right there. There's a 28750, that objective value. That was our revenue that you see. Pants 375, jackets 250. So that would have been a lot quicker than going through and solving it like we did today. Then out the data, we're going to get all the different variables that we introduced into the optimization tool. And then we also have our interactive report as well. Our interactive report, it's going to look like this. It's really going to contain all the information that was in the S and the D, but presented in a nicer, easier to consume way. One thing I do want to call out, you can see the red on the bottom right-hand side, the slack. That means that we didn't waste any cotton or polyester. There were no leftover square feet of cotton or polyester. So if that number was positive, if that slack was positive, that would mean that we had some leftover fabric. All right, so with that, let's flip over to Alteryx and let's see what configuring this actually looks like. All right, so here is our workflow. There is the prompt that we fully understand. I have no doubt after what we've just gone through that you guys could recite all of that back to me right now. For simplicity's sake, I've minimized this tool container. We'll take a look at that here shortly when we talk about modeling as matrices. But let me zoom in a little bit here. You'll notice on the left-hand side that these anchors are gray. As you might know, that means that they're optional inputs. We don't need to feed anything into them because in our example, we're not feeding anything into it. Everything is going to be configured on the left-hand side. So let's look at that. We went through all this in the PowerPoint, but I want to click around and show you how you would actually enter this if you were to solve this problem. And hopefully after today's session, you guys all will be able to use this optimization tool. So I want to make sure that you understand how to configure these. So the first choice, entering the model manually. You can see that you could also enter it as matrices or from a file. We'll talk about matrices here later. The program type is linear. We do have some other options. And then, like I said earlier, there is another solver. We're not going to discuss the differences in solvers today. This is where we make sure we're maximizing the objective. And then the 3 tabs on the bottom. So our variable list, we entered X and Y. If I wanted to add another variable, let's just say I wanted to add Z in here, I can just separate it by a comma, and then I need to click the plus button. Once I click the plus button, it will then go down into the objective. So then I can actually reference it in the objective. So let's just say it's 100 Z. And if I zoom in for you guys, you can see that the variable is blue in color versus the black of the coefficient. So that is how you add a variable into that objective function. And remember, the objective function is what you're trying to maximize or minimize. $50 for every pair of pants, $40 for every jacket. Let me remove Z as well. Our constraints, these were our cotton and our polyester constraint. So let's just assume that we had a constraint for Z. Maybe it was Z has to be equal to 100, make it nice and easy. And if I then click the plus sign, you can see only when I click the plus sign does it get added. So always make sure you click that plus sign in order for that change to be reflected in the configuration window of the optimization tool. I'll go ahead and remove that again for now. And then if we go on to the bounds and types, this is where we chose based on what we just entered there. So you can see it still has Z reflected. Since I added Z, Z doesn't exist, so I'll go ahead and remove that. This is where we would enter in those lower and upper bounds, as well as what type is it? Is it continuous, binary, or integer? In our example today, we're using continuous. So really, that means that we could produce a portion of pants or jackets. That's obviously not something that's possible. So we probably should have chosen integer in these examples. All right, so let's look at the outputs here. So the output from our S, I'll just show you what it looks like down below. There is our 375 for X, our 250 for Y, and our maximized objective value. That was the revenue. We have all of the details about the inputs, the constraints, the objective value, things like that. And then on the left-hand side, once I click on this browse, we will see the interactive view. All right, so pretty easy stuff now that you guys understand what needs to go where. Let's look at what this would be if we modeled using matrices. So rather than entering the values in like we did manually in the configuration window, what if we used matrices? And before we start to talk about the configuration, I feel like it's important to address why would you want to use the manual mode versus using matrices. So let's compare those two methodologies. And for those of you that are reading ahead, just know that the bullets compare side by side. So the top bullet on the left using manual mode compares to the top bullet on the right using matrices. So if the model is static, it's a good time for manual. If it needs to be dynamic, so for example, let's say that one week we have 1,000 feet of polyester. The next week maybe we have 2,000 square feet. The next week we might have 2,500 square feet. If that is constantly changing, I would want data to be fed into the optimization tool so I don't have to go and manually change the value each time. So really, anytime something changes, anytime constraints are going to change, the optimization function or the objective value is going to change, really any aspect of anything that we've talked about today, anytime that's going to change, we're probably going to want to use matrices. So let's talk about the anchors when we use matrices. So you can see we have 4 anchors on the left-hand side. We've got O, A, B, and Q. So with our matrix, if we're solving using matrices, we do need to use minimum 2. More often than not, we'll use 3 of these. The one that we won't use is the Q. The Q is used for quadratic programming problems, so not one we're going to talk about today. The O anchor. This is where we provide the names of the decision variables, their coefficients in the objective function, and optionally their bounds and types. So in our example, it's 50 is our coefficient, and 40, so 50x plus 40y. That's what we would put into the O output. The A anchor, sorry, actually, let's dive into that a bit further before I go and talk about the A anchor. So in our example, we have 2 rows because we have 2 variables. We have pants and jackets. We have a column for our coefficients. That's the price for our pants, the price for our jackets. We have the type. The type is whether it's continuous, integer, or binary. And you just use the first letter of each of those words to tell the tool which type it is. And then you have 2 columns, LB and UB. That's the lower bound and the upper bound. The lower bound was the minimum we could produce. For pants, we had to produce at least 200. So that's why our lower bound in the first row is 200. The upper bound, we didn't have a maximum we could produce. And so that's why we just put INF. That stands for infinity. We could, according to this constraint, produce an infinite amount of pants. Jackets, we obviously have to produce minimum of 0, so lower bound 0. Our maximum, according to the business rules, was 400. It is important to note that these names, variable coefficient type LB, UB, make sure you're using those names as you're seeing them here. The A anchor. So the A anchor, we're going to put in our constraints. So for pants, it was 1 square foot of cotton for every pair of pants and 2 square feet of polyester. For jackets, it was 1.5 square feet of cotton and 1 for polyester. And then how that matches up with B is for B, you can see that we have 2 columns, DIR, which is our direction, and RHS, which stands for right-hand side. So the value that's on the right-hand side of the equation. So if you take the first column, I should say, if you take the second column of the chart above, the LHS, it's colored in green, and that's the cotton. So for cotton, if we make 1 pair of pants, we take 1 square foot of cotton. If we make 1 jacket, we take 1.5 square feet of cotton. That corresponds with the first row of what's going into the B anchor. So the 1 times pants plus 1.5 times jacket has to be less than or equal to 750. So that's why in the matrix that's going into the B anchor, we have less than or equal to 750 broken out. So again, hopefully you guys can see how that's illustrated in those two different matrices. You take the left-hand side in a column, that same equation then is in the row of the right-hand side. All right, so now let's go head over to the Alteryx Designer and see what this looks like if we use matrices. All right, so let me zoom out for you guys. Let me open up this tool container to expose our matrices. And this should be what you all saw earlier. So here's the objective. We have 50 as our coefficient for pants, 40 for jacket. We're using type continuous. Like I said earlier, we probably could have used integer. We get the same result regardless. And we have our lower bound and upper bound. If I look at the matrix going into our A anchor, again, these are our constraints. So for pants took 1 square foot of cotton and 2 of polyester. Jackets took 1.5 square feet of cotton and 1 of polyester. And then our bounds, which is really the rest of those equations, needed to be less than or equal to 750 and also needed to be less than or equal to 1000. And so that gives us the exact same answer. So you can see that we have our pants at 375, our jackets at 250. So all the rest of the information here is going to be exactly the same. Remember, the benefit is that if our values change in this example from week to week, we want to use matrices. If it's going to be static, we can use the manual mode. I'll make another quick pitch for the community and the academy. Community.alteryx.com, academy.alteryx.com. There's a lot of great content out there. One thing I didn't mention to you already was our virtual solution center. So if you want some one-on-one advice or just help solving a problem, if you go to community.alteryx.com /VSC, which stands for Virtual Solution Center, you can book some time one-on-one with an Alteryx professional. So yeah, we'd love to see you in that Virtual Solution Center. And so with that, I hope you all learned something today. I hope you understand what the Prescriptive Optimization tool does inside of Alteryx, and that you now know how to configure it. You know what types of use cases can be solved as well using the Prescriptive Optimization tool. I want to thank you all for your time and attention today.